Another draft physics presentation. Yes, on the slit experiments, mostly the single slit or the no slit at all, as the image indicates. I'll go into a little bit more detail of what I think is a possible explanation or something along the lines of, and that kind of thing. So in this image, this is just a razor blade, and you can see the shadow of the razor blade. So maybe it was 2 feet away from the laser, and so you can see a lot of light. It does come out kind of funky out of the laser. And I add my finger just to knock out the bright spot. So I put my finger about 10 inches from the target that might have been a couple of meters away, and just to knock down the brightness of the bright spot for the purpose of taking the picture. But you can see there's a bunch of a halo of diffracted light, different kinds of crap, and that just is in the laser all the time. I mean, it always diverges coming out of the laser. It has some scatter associated with the laser, so 95% of the light goes straight, and the other 5% goes all kinds of places. But it does create for an interesting concept when you just think of sizes. I mean, that image is on a piece of paper, so that the razor blade is now 10 inches across or more. And it's just a razor blade, and we're talking about 2 meters. So you can get quite a bit of magnification out of light. So certainly the idea that light spreads diverges. You can understand how that could magnify a signal, like in the interferometer, and that it really wouldn't have anything to do with the frequency of the light. It would have to do with the divergence of the light. So I know that's a different subject, but it's all light, and so it's all sort of related. Alright, so anyway, so the beam is just coming over the horizon of the laser, and over the horizon of the razor blade, and it creates a little spike, and then the spike can be maximized to a pretty significant length, a couple of feet, and it goes in both directions, which I thought it should. The reason it didn't in my previous experiment was I used a loop of metal, and so the diffraction was created by the first piece of the metal, and then the second piece blocked, obviously, the bottom part of the diffraction. So that was my error. Alright, and so I guess we'll just to suppose this against, I'll play the Professor Lewin clip of the standard single slit pattern with a opening that comes and closes in on a laser beam. And the interesting part is that there's a certain point, like I say, some light will create some diffraction, but you really need a certain amount before you really get a good spike. And this spike essentially represents what is the single slit pattern spike. There's just no pattern in it because it's one slit. So one could argue that both surfaces of the single slit, the two surfaces, are both creating the same pattern, just a little bit offset. I think it's a reasonable statement. So on to the videotape or whatever, right? I think this one has to go up, I think. Yeah, there it is. Alright, so this is the other thing that was interesting. Well, I'll go back to the image just for the another thing that was interesting part. Anyway, we'll just play this. I'm going to turn the sound off just so I don't get any echo, because I don't have the earphones in and all that stuff, because I didn't plan on playing anything. He doesn't say anything terribly interesting here. So this is just what it starts with, and then he brings the two slits into the beam. And so it'll start stretching from the middle out. And you can already see bars there. I mean, I can see them. I'm pretty far away. They're pretty clear. And again, they're bars. Okay, this isn't the pattern you're supposed to have of gradual on and off, sine wave kind of on and off. It's a very barish pattern. So more encroachment, and so I would argue that this is the same circumstance as the single slit for each individual surface in a sense, because it's longer, but it still is curious. It has to do with how much light is getting across the surface is dictating how wide the slit goes, and so it gets kind of complicated because obviously as you make the slit narrower, you're changing the amount of light. So instead of having the same amount of light, you're changing how much light can get through, and therefore the two are working against each other, where when you have an open slit, there's nothing stopping the extra light from participating. Something like that. Alright, so the pattern gets wider and wider again. No no obvious sine waveness to it at all. Very harsh darks, very even, and surprisingly even lights. I mean, the lights don't have a center point that's really, really bright and fade off as they should. And likewise for the darks. The darks, very little blending into the light sections. And by their theory of wave, those should be very gradual transitions. And they're not, quite obviously. And so he can crank it down to very, very small, thin slit. So it gets wider, the pattern, but in a sense the divergence isn't getting wider, the pattern's getting wider. But they can be thought of as sort of the same thing. And he stretches this out pretty far. So that would represent a foot, say, in his experiment, and you've almost lost everything else, and all you have is the central maximus that's left. And again, it's very bar-shaped, and that would probably be an indication of just the fact that there's so little light that it's no longer scattering from the top and the bottom, because there's so little light. And so that's making it more and more linear, I suppose. Something like that. I don't know. These are questions they haven't bothered to answer. But you can see in there also that the pattern does have a distinctively not square. It's got this roundness to it. It's right in here somewhere. Come on. No, I don't want it in there. I want more. I want more. Oh, that's right, it went backwards, so it's confusing me by going backwards. I mean, made it wide and then it goes back to narrow. Oh, let's go in here somewhere. There you go. So, I'm going to move it forward a little from there. But you notice they're rounded. They're not at all some better geometry. Okay, so, go back to this thing for one little bit, and then we'll move on to drawing and such. Maybe I'll magnify this a bit if I can. Let's see how that works out. So you can see these extra lines here, which I found kind of interesting. And I don't know exactly why. They seem to have very uneven separations. Why there'd be certain points where there's enough light to make a new beam. So it is kind of interesting that we have diffraction in this direction when there's no real reason to think that should be caused. Now the razor blade is crappy. I have to concede. it's not pristine, so maybe this is an effect of defects in the edge of the blade. But clearly the middle has the very strong beam. And regardless of what condition it was in, it creates the very strong beam. So I don't really have an account for these extra lines. So if somebody else has a guess, fine. But I don't have one. I just sort of indicated one, but I don't have any confidence that it's anywhere near the truth. Yeah. Alright, so let's move on to drawing, right? Yes, that's what I want to do. That's it. Okay. Alright, so where to begin and how to begin. So first, the idea is the narrower the slit, the wider the divergence, and the wider the slit, the narrower the divergence. That's one rule. I guess what would be interesting is if in the Professor Lewin example, if they moved the slit into the beam of light. So, had this steady beam of light and just move the slit slowly across it to see what the effect would be. That might be interesting. Maybe I can duplicate something like that. Because again, it is curious that the single surface, so that's just saying one of these surfaces, creates a strong pattern. Okay, no bars, but strong pattern, strong divergence, strong spread. But at a specific amount of light has to be over the surface. So just a little light doesn't quite do it. The right amount of light does it. Interesting or not interesting, not quite sure. Alright, so the basic idea is you have two surfaces. So that's how we'll try to understand this. And we have to come up with a reason why some percentage of the light, a specific percentage. So we know that like 90% of the light goes right here. So it ends up in this, right in the middle. So 90% of the light, and the slit is very small. So the slit is the same width as, less than this bar of light here. So you can understand that if a photon went straight through here and didn't get interrupted, went on a straight path, and it went on a straight path here, those straight paths would be inside this distance. So you have to understand that these could just represent, the ones in the middle could just represent photons that don't hit anything. They just zoom right through, completely unmolested, and those are the ones that end up in the middle. And so then you have the rest of these patterns that have to be explained for why do some of the photons end up someplace else, over here or over here, and they end up in specific locations. Alright, so I've pointed out before that in the math the sine theta thing is just an angle, and angle x, and basically they just multiply the location as a number, and they just multiply the number times the value of that sine theta to get why light is in those locations. So this is the thing in the variable. It's just assigning a variable, and that just targets things. So I've sort of argued that what's happening is there's a number of electrons, in the field surrounding any surface. So if you have a single surface, the electrons are free to the external world. That is, there's no obvious charged element around them, so they'll be the most relaxed, in the sense that they're feeling the protons that are inside the material. So the protons are inside these atoms, and they're feeling the repulsion from the electrons. But the proton force is stronger than the electron force, and so they have an affinity for the area, but they don't like each other. So if there's going to be a tendency to fill the area by a certain, there's going to be a tendency for them to be equidistant, and to find locations where they can get as close to the protons and stay as far away as many electrons as possible. So, but the pattern can be rather chaotic when there's no interference from any other surface. So I'm sorry that's in the shade, but Maybe I can fix that a little bit. Ooh, sorry, microphone. I still didn't fix it much. Yeah, that doesn't help at all, actually. Alright, well, I'll just have to draw bigger. So I'll remember that next time. Yeah, next drawing. Alright, so what I'm arguing, so that's for when it's relaxed. So when there is another surface, what's happening is these electrons over here are going to cause repulsion to the electrons over here, and so these are going to start to become more precise in their location. They're going to start getting more ordered because they're going to be pushed under pressure, so now they won't be able to be nearly as random. Now what I'm speculating is happening is that as light goes through these electrons, if it hits an electron, it moves that sine theta thing. Okay, it moves that angle, a specific angle based on this distance, which is the pressure distance. So as this distance changes, the angle at which the photon will leave is changed, and the amount of variance in that angle changes. So the angle could be 1.7 degrees or it could be 1.5 degrees. There's a range, and as you tighten the photons, that range increases. So that's sort of an important feature, because we have to explain why the pattern goes from this to this. Okay, it stretches out, and that means that the variance in the angle has to also stretch as the slits are moved towards each other. So my argument is there's an angle that these electrons, when you hit an electron, you'll be moved by that angle, and that'll dictate your trajectory. So if you hit one electron, you go 1.7 degrees. If you hit a second electron, okay, from that, so you hit another one right here, you'll go another 1.7 degrees, and that'll take you out to another location. Or it might be 1.5 degrees, so that's the variance, and that variance increases as the slits get closer together. So when you see a pattern that has a bunch of bars, I would speculate that that's representing some measure of the thickness of the electrons, how many rows of electrons there are. Because you technically would kind of have to have rows, because you'd have to have the ability to hit one, go 1.7 degrees, and go 1.7 degrees, go 1.7 degrees, go 1.7 degrees. You'd have to have the ability to hit quite a few to create these outer bars. So that would mean that you hit 25 electrons. So as the slits are still wide, there's still lots of electrons. But as you make the slits narrower, the electrons are very repulsive, and what they start doing is leaving. So they start just saying, the hell with you, I'm getting out of here. And they go over the edges of the material. They won't be that close to each other. So the actual number of electrons starts to decrease as you decrease the slit width. And there's a second consequence to that. So that reduces the possibility of doing something where you shoot out 15 interactions worth, having so it just says that you can't do this 1.5, 1.5, 1.5, 1.5. I'm doing a very poor job of well, 1.5 degrees is really hard to see, but you can have this little degree change, and you could have it for like a 45-degree angle. There could be 45 increments to get to that angle, something like that. So where's my other piece of paper? It's probably underneath this one, which isn't too bright. Okay, so anyway, so that's the pressure argument and the number. So you're changing two factors. So you're changing, when you narrow the slit, you're changing how many electrons you can hit, and now they're under more pressure. So they're going to end up being at their maximum, say, pressure or whatever it would be. And that's what's causing it to go wider and wider. The pressure between these electrons is getting stronger and stronger. They're getting pushed tighter, closer and closer to each other. They're probably in some sort of order like this, where they're stacked on top of the empty spaces. The geometry is probably something like that. Electron here, electron here, electron here, electron here, and it's almost like a xylophone. So you can see how the compression forces, as this one gets closer, these two have to be pushed out, but they don't want to be pushed out because they're still attached to this proton. And now that they're compressed, they're even closer to the proton, but they're also closer to these other electrons, which they don't like, so the tension's getting stronger and stronger. So when a photon hits an electron under tension, it's going to move it in a different way. So the theory of how these electrons move, and my point would be, is that what happens to the electrons is when they get hit by the photon, they don't move in a straight line unless the electrons are very relaxed, because there's no pressure on them. So there's no other electron around. Then this electron gets hit by a photon, it just moves in a straight line. But if it's under pressure, it's not going to, first it's going to be, so it's let's say it's a straight line, but there is an electron way over here. So even though it moved in a straight line, it's still going to feel the pressure of these other electrons that are in the field, and it's going to want to go back to where it was. And the going back process is where it releases the photon. So if it moves straight from one position to another position in the same line of momentum as the photon that hits it, and then the electron moves back to its position and releases the photon, you get the idea that it's going to be in a straight line and there's not going to be much effect. But if it's under pressure from the other electrons next to it, what I'm arguing happens, I'm drawing them bigger for fun, is, okay, so the photon comes in, it hits the electron. The electron, because there's other electrons in the way, so there's one here, let's say, and there's one here, it moves in a semicircle. It feels the pressure of the other electron, it avoids that field, and therefore bends, and then when it goes back at an angle, and that's the new angle. So that's your sine theta. That's your angle per impact. And when the more pressure it's under, the more eccentric that line gets, the more crooked it gets. So the more these are compressed, the more this line gets crooked, and therefore that increases the angle. And it also increases, because of variances, the spread of that angle. So the angle might be 1.5 degrees, and it might have a spread of 3 degrees. So it can be anything 1.5 degrees on either side of that 1.5 degrees could be the spread, because the arc can be that uneven. Because of the pressure being depending on what electron you hit and what position it's in, it'll spread different amounts. So all the photons that just hit one electron in different positions, this position versus this position, which will constitute the spread differences, the angular spread differences, and all of those will end up as the blob, there. The one not in the center. Now, why the center ones start spreading, that would also have to be explained, as hitting one electron probably does create. You're still in the central maxima ballpark. So the central maxima is probably made up of all the. That's why it's bigger. It's made up of the light that goes straight through and doesn't hit anything. That would be the middle part. And these two end fringes are really these two fringes. They're really the first one electron hit. positions, and then this would be 2 electron hits, and then there would be 3 electron hits. Oh, that's not on the paper. Well, it was on the paper, but it's behind the image. So what I'm arguing is that if this is the slit, and you hit 1 electron in any one of these positions, you can sort of understand that the angle from here is going to be subtly different from the angle from here, so that's going to create some spreading. So you go 1.5 degrees this way or 1.5 degrees that way. And you can understand that from these 2 different positions, that means you're going to get some blurriness. That means that it's going to have a wider arc. And the argument is all the ones that miss go straight to this middle. The ones that hit 1 electron go here or here. And then the ones that hit 2 electrons go here or over here. And the ones that hit 3, and on and on. And depending on how compressed it is, how close these 2 slits are, that increases the angle because the arc of the electron gets higher, so the divergence increases. I think that can account for the phenomenon substantially. And you don't need, see, their theory is we'll do their theory real quick, I suppose. Something like their theory. I mean, it's almost impossible to explain their theory because their theory is that you have this opening, and what happens is a photon goes in, and somehow, by this Huygens rule, because this is a confinement, somehow it breaks into 2. Okay, it turns into 2 now, so it comes in as flat waves, and it breaks somehow into 2 separate curved waves that somehow interfere with each other in some way, and then the actual photon ends up just going to 1 location by probability, by rolling the dice. Somehow the photon has dice. It does this thing, it rolls the dice tell it where to go. And I don't know what their argument for the single slit would be. I mean, a single surface. So, oh shit, sorry. My bad. So the light comes in, flat waves, comes out as 2 separate new waves that interfere with each other, and then the photon recollapses into a single photon. And in here, the photon doesn't even know where it is. So this is Heisenbergy. So it doesn't matter whether the photon goes right down the middle, or it doesn't matter whether it goes right next to the surface. It rolls the same dice. Same dice are rolled. This doesn't matter. If you could stop all the light, theoretically, if I could stop all this light, just make it go away, they would argue you get exactly the same pattern. Because it's all just probability. It has nothing to do with where the photon actually went through the slit. Alright, and in this single surface, I don't know what their argument for Huygens would be, but somehow flat waves go in, hit the surface, and somehow, it turns into a round wave, and somehow the round wave decides, it spreads essentially. So the round wave just essentially spreads the light, no pattern. And then in the double slit, they make up a new story. That the wave comes in and it gets broken by this middle impediment into these 2 separate waves. So it's like here with 2 waves, but not explained. See, if you Huygens here, then you'd have 4 waves. See? I mean, Huygens would mean there's 4 waves, and they don't have 4 wave interference. So somehow in the 2 slit it knows no Huygensing. Don't Huygens, because that'll screw everything up. I mean, only Huygens in this way, where you round your wave off. But don't Huygens in the way where you created 2 waves in 1 slit, because that'll mean you'll screw everything up. And so I'm just saying this is kind of irrational. To say that it doesn't matter where the photon goes in, that they don't know where they are, they end up as a little corpuscle at the end over here, and somehow they turn into a bunch of ambiguous blah blah in here and interfere with each other. When I think you can make a perfectly rational argument that it's a mechanical system. They're actually hitting billiard balls, so to speak. There's no magic to it. And as I pointed out before, this argument explains why the electrons have the right pattern. In the sense that the electron pattern, when you do the experiment with electrons, you do get a sine wave. You do get a gradual on, gradual off pattern. Okay, so this would be light and dark. So it would be peak light, peak light, peak light, peak dark, peak dark. And in electrons you get that. And you get that because when electrons are crashing into electrons, they have their force fields. They're emitting, back and forth their photons. And they're bouncing off back and forth. So they have pressure. So they always take a curved path. They don't bang into something. They curve their path based on the force. So that's why it comes out much smoother, is because the path of the electron, if this electron was over here and interacted with this one, it'll curve much wider than if it comes in head on. Then it might go straight. And then if it comes the further out it goes, the less it curves. So that's why you're getting a gradation in the pattern. So I don't think they have a Huygens explanation for that difference. I don't think they have an explanation, period, for why the electron pattern is this nice, smooth, gradual on and off, and why the photon pattern is so much more barry, very, very faint, just very little noise, very little gradation, very harsh, very bright, very consistent, same brightness across these things pretty much. Very little, no peak brightness in the middle, nothing like that. No sine wave, plain and simple. So I don't think they have an explanation for why the electron's a sine wave, photons no sine wave. Where I think I just pointed out the big difference between a photon hitting an electron, which is it's a full momentum experience. The photon reflects right off the electron, and the electron gains momentum from the action. And where in the two electrons meet, they never hit each other, and their momentum is diverted by not only the movement of this electron out of the way and the movement of this one. They push each other gently out of each other's way. So completely different mechanism. That's why you have the different patterns. And their physics, their theory says same mechanism. They pretend it's the same pattern. It's not even close, but they just pretend. And look, they also are saying that an electron with a velocity has a frequency. So it moves 50 miles an hour. We're going to give that a frequency and call it 50 hertz or whatever. So they're saying something is going a perfectly straight velocity. It doesn't have any interruptions. It's not like one electron is there and one electron is there and one electron is there. No frequency at all. They're just saying that a single electron moving 50 miles an hour has a frequency. And just to make their math work. They're creating a fake frequency that doesn't really exist. They're associating the momentum of the electron, which is linear and straight, with the effect of something at a frequency in terms of the way it can affect things. In the sense that it hits it and then hits it again, and the period between when it hits it will create a difference in how it moves. That was something I didn't really get to, but so I better get to it. New piece of paper, I believe. Oh, boy, I'm really squandering it. I only have about 1 billion pieces left. Yeah. I'd like to finish this before I run out of paper. That would be really cool. Anyway, I'm going to finish this whole project. I'd like to move on, but can't really do it until we finish this shit. That means crap. I mean garbage. Alright, so the argument is, so let's say this is the electron in red, just to make it clearer. And the photon has two elements to it. This is its frequency, or its wavelength. You know, the distance between them. And the point would be, as I pointed out, it doesn't move in a straight path. So if it does move in a straight path, yeah, it's just 2 hits. You get 2 hits worth of momentum. But if it moves at a curved path, you can sort of understand that if this is moving, and then the second one shows up, that it's on a curved path, that when the second one hits, it's going to hit with a different momentum, because it's hitting it as it's moving in a direction. And so that's going to, perhaps, it'll change the angle at which it turns. So that's why frequency is important, because the faster the frequency, the higher the frequency, the more tightly bound they are. The further away they are, the less it matters. The faster the frequency, the hits are hitting as it's turning, and that has more effect in terms of creating more change in the angle at which it will be affected as it's getting hit. So that's why the frequency of the light changes how much the pattern, how tight it is. So the higher the frequency, the less spread in the pattern. The lower the frequency, the more spread in the pattern. Because the higher the frequency, this is a tighter cycle, and the direction will stay. The sooner you hit it, the less it's moved, the less angular change. So the quicker you hit it, the less off this straight line it can go. So if you hit it really quick, both of them end up straight. But if you hit it a little slower, this one's already changed its position, and that means you are going to compound the change in its angle. So the slower the hits come, the more effect you have on how much of an angle the sine theta will be. Alright. So I'm just using the sine theta is that they have a mathematical formula, the wave formula, and the only feature of it that's important, we're agreeing that the distance matters, we're agreeing the width of the slit matters, we're agreeing the frequency of the light matters. Those are all constants that we're all agreeing on. The source of this angle, that's the thing I'm arguing with. They say it's Heisenberg and Huygens. They say it's this uncertainty probability Heisenberg crap plus this Huygens bulging wave crap. Yeah, might as well. And it really isn't. Okay, it's you don't have to believe that. You don't have to believe in that crap to assign a value to the sine theta. It can be assigned based on just understanding that the more stuff you hit, and you're moving a specific amount each time you hit, that's going to give you exactly the same results. Alright, I think I've done my job here. So, comments basically welcome, but I mean, I'd like to have a discussion with somebody who wishes to defend the Heisenberg-Huygens interpretation of the two-slit experiment. Then we can get into the other Copenhagen and many worlds and all of the other stuff they've invented as a consequence of this experiment, as if they have to explain how this collapsing of the wave function happens because they created a wave function. It's not something innate in the photons. The photons are doing what bullets do. They're coming fast or they're coming with a distance, but the distance is changing between the shots. But that's all that's happening. There's no wave function here. Alright, so I mean, so I'd like to have a conversation with somebody who wishes to defend conventional physics' not only their understanding of what's actually physically happening in the experiment, but then their preposterous interpretations of the consequences of their Heisenberg and Huygens theories, which end them in creating nonsense where photons can read minds and photons create universes and all this other mumbo jumbo. Photons have a complex radar system and, you know, dice to roll. So anyway, till next time, such.